plots for each of the triplicates against the reference monitor. And then, we might provide other time averages. So yeah. And then at the end of these reports, we'll typically provide like a summary table. This is more for, we kind of have to balance how we present information because we have like two communities of users of our information. One is like kind of the community people, the lay persons who are not very technically knowledgeable. They kind of just want to know which one's good. Just tell us that, right? But for the more technical, for the more scientists among us, it's not that simple. You can't just say that this product is good and this one's bad. It's like, well, what is it good at and what is it not so good at, and how good and how bad is it at? So for the more technical audience who are interested in our reports, we also provide like a table where we show for each time averaging that we do, what are the average and the standard deviations of the sensors and the reference, what is the R-squared slope intercept, and then the mean bias error, mean absolute error, and then root mean squared error. And we also provide similar metrics for our reference monitors too. So that's a little bit more detailed information that we put at the end of the report, for scientists and stuff. And because we've tested so many sensors now in the field from our 10-year program, we're able to kind of aggregate all of our observations and make some general some observations about the state of the industry, right? So over the years, we've noticed that of the PM 2.5 sensors that we've tested in the field, the average R squared of the ones we're testing every year, it keeps going up and up and up. So the PM 2.5 sensors, they're getting better overall in general. So I'm confident as we keep going in time, maybe we'll eventually get PM 2.5 sensors that may be just as good as what we consider to be reference monitors if we see this continued improvement. And then at the same time, we're also seeing mean absolute errors in the sensors that we've tested also go down in time. So that's also really positive news that their biases are decreasing. And then the only other one that I see as I don't want to mention negatives, but I want to mention positives. Another positive I see is NO2 sensors. So their R squared in time that we've been noticing is that the ones we've been testing, they've also been getting better. They used to be horrible, no correlation whatsoever. But we start to see them. They've almost passed the 50% mark, the mark at which, is an NO2 sensor, is it a 50-50 shot at whether it's telling us a correct value? Here's another way to look at the overall state of the industry of sensors that we've tested. So, the field performance of the PM sensors we've tested, it generally degrades as the particle size mass fraction increases. So basically, PM1 sensors that report PM1, the gray points, they're typically very close to reference monitors that report PM1. So their R squared is typically, pretty high, almost 0.9, or sorry, 0.8, on average, 0.8 of an R squared for the PM1 reporting sensors we tested, and also typically the lowest average mean absolute error. And then when you look at PM 2.5 sensors, they're not as good, but they're still quite good on average, an R squared of 0.7 and then mean absolute error of 7 micrograms per meter cubed. Now, the problem is when you look at the state of the industry for PM10 sensors, on average, the yellow plots, they're still kind of in the danger zone where their R squared is below half. So they're not really explaining much at all about, real realization so far. Let's see. So ozone metal oxide sensors, that's a very promising area where on average we've seen a R squared of 0.8 and 14 ppb as a mean absolute error. I think for Los Angeles area, because we have such high ozone levels, 14 ppb is not that bad, I guess, for a low cost sensor. But for many other areas where their ozone is probably not that extreme, that might be a problematic mean absolute error. I think another bright spot is the carbon monoxide electrochemical cell sensors. We're seeing on average R squares of 0.7 and mean absolute error of 130 ppb. Now, that might look high, but it's actually not, because carbon monoxide, we typically think of carbon monoxide on the scale of ppm in the ambient air. So, 0.13 ppm when your ambient CO is maybe, 1 ppm. That's not terrible at all either. So there's a few promising spots we're seeing in the gas sensor space as well. Okay, moving on to lab testing. So we reserve lab testing for sensors that performed well in the field. And the reason is because lab testing is very money and staff intensive. So what lab testing does is it exposes sensors to controlled conditions. Really, it's for clearer investigation of the extreme conditions and for interferences. So in the field, you have a complex atmosphere, but the 8-week period that you test, you might not get very high values of the pollutant, or you might not get a huge range that you got to test them against. So the laboratory lets us pump in pollutants to achieve incredibly high concentrations to kind of see how well does it perform if you have very high concentrations, or how well does it perform if we make it very humid in there, or very hot in there, or very cold in there. Also, if we intentionally inject interfering species, that also lets us see what the effect of that is. So for example, many, I guess, NO2 sensors, they experience interference from ozone. So in the field test, you're not really guaranteed, optimal conditions to figure out this interference effect because it's all mixed together and it's all kind of moderated. But in the laboratory, you can very tightly control, okay, we're going to put this much NO2 in, and then we're going to put this much ozone in, and then we want to see a clear effect on the sensor from that kind of interference. Okay, so sensors, they're mounted alongside the chamber, mounted inside the chamber alongside our reference monitor probes. So this is a view of the chamber that we use for testing criteria pollutant sensors. And so you can see that's like a T640, our sampling probe for the T640. And then there's some, it's hard to see, there's some gas probes on the side wall that go out to our gas monitors. And so you can see an example of sensors that are mounted inside the chamber. And we do it in 3 phases. First, we do a 5-step concentration ramp. So we just like do our pollutants like this, higher and higher. And then in the next phase, we try to see what the effects of climate are on the sensor. So we'll do 3 temperatures, 3 humidities, and 3 concentrations, and we'll do every single permutation, I guess. So that's like 27, sub-tests in phase 2. And then for the gas sensors, we'll also do an interference test to see what other gas species affect their performance. And so these are a lot of similar metrics that we report as the field evaluation, but we'll also, talk about the performance in different climates and, talk about interference effects. So for these two, we don't really provide something super quantitative. It's just more about a discussion of how these variables impact their performance. This is just a list of the reference monitors that we have available in our laboratory setting. So, we do use a T640 as well for our reference particulate mass. And then we've got particle size distribution data for, ultrafines, and then for, your larger size particles, as well as for the gases. And then I'll just walk through what a typical lab test report looks like coming out of AQ-SPEC. You have a cover page, a background information about, the past life of this sensor. It was deployed in the field from that day, because we do want to be upfront about they went through the harshness of being in the field. And so they're a little dirty and aged. And so when we bring them to the lab, there might be a little bit of that aging effect on them. And then also any notes like this one, this particular unit did not transmit data during the lab tests, except for certain experiments. So just some background, so, the manufacturer provided information about the sensor, and then, the information about the reference monitors that the sensor was judged against. And here's some example, time series and, scatter plots that you'll see in our lab reports. So, in the lab experiments, they look a lot nicer. Like the time series are super clean, like these steps. And accordingly, most sensors, they'll also perform very clean looking in these lab tests because, again, it's a very simple environment where there's no other interferences. And so you'll usually get, regressions that are very nice and linear, a very different picture from the field reports. We'll also provide some, other metrics of accuracy, because it's a little easier to calculate these metrics when you're in a much more controlled setting. Some precision. This is just commentary on precision of the three sensors when they're at each of the 27 different climate combinations. Most sensors, they're pretty precise no matter what. They agree with each other no matter what climate you put them at. It's more about the accuracy that gets affected when they're at different climates. So here's an example. You can see, if we do 5 Celsius and 15% RH, so very cold and very dry. And then we have on the opposite end of the spectrum, 35C and 65% RH. So, pretty warm for I guess Californians, hot and hot and humid. You can see how, the sensors, which are the green, yellow, and blue, and when it's cold and dry, they're underreporting against the reference. But then when it becomes hot and humid, you can see the baseline, went up a lot, and the response is very different. And if it's a gas phase sensor, we'll also show the interference effect. So this is for the ozone sensor, and then when we inject NO2 as an interferent. So our reference ozone monitor, that's our ozone. It's very stable throughout the entire experiment. And then the three sensors that only two of them actually were working on this one. So the two of them that were working, you can see their response. And then we have our reference NO2 measurement where we inject NO2 while the ozone is constant, right? So you can see in this case, the sensors went up along with the NO2. So even though the manufacturer is like, oh, this is an ozone sensor, it's very accurate, it works great. But in reality, if you were to also, have the influence of NO2, they would also be partially responding to NO2. And then here's an example where, the ozone sensor is not sensitive to SO2. And we typically don't expect it to be sensitive to SO2, but so again, you see the red is our reference monitor ozone, and then the green and the yellow is our sensors that also staying, in a good agreement with the ozone reference monitor. And then we inject the purple, we inject SO2, but the sensors, they still stay flat. So they're not being affected by the injection of ozone into the chamber. Okay, our latest effort now is to test VOC sensors. VOC sensors are the hot thing. They're the cutting edge of low-cost sensors now. And we test them in the lab first because VOC is kind of tricky to test in the field. Ambient concentrations of VOC, at least in the United States, is pretty low. So maybe we're talking about 0.1 to 0.3 kind of ppm levels. And so for a lot of these low-cost sensors, they're probably not going to see anything if we put them in the field first. So you put them in the field and you leave them there for 3 months or whatever. You might not really have any meaningful results to judge their performance against. So we decided to, the opposite of criteria pollutants, we're going to put VOC sensors first in the chamber, and then maybe if they do well in the chamber, maybe it's worth putting them into the field later. Because in the chamber, we can, create very high concentrations of VOCs to actually see if they respond. So this is the setup of our laboratory VOC chamber. So we have our regular chamber space, and then we have a secondary inner chamber space, which is very tightly sealed for our safety because we don't want to be breathing in the benzene that we pump in. And so the sensors go into this hermetically sealed inner chamber space. And so the inner chamber is where we pump in our zero air, our humidity, our heat, our cold, and we also pump in our VOC gases. And so here's an example of a triplicate of VOC sensors that are going to be sealed inside this inner chamber for testing. And, you might have noticed that our field testing was, very simple, 8 weeks in the field. And then our lab testing was was 3 phases, right? A ramp, climate conditions, and interferent. And then our newest testing protocol, you can see it has 6 phases because, as we go on in time, we just make things more and more complicated because more people want to know more details about how these things perform. So we have a 6-phase test result where we do a ramp. Sorry, let me take that back. The first phase is a transient event test. It's just a nominal spike test. We just puff a bunch of VOC, see if it even responds at all. Because if we don't see any response just from simple puffs of VOC, it's not worth investing. It's not worth putting in more staff time and resources to do this expensive lab testing.